Welcome to today's Explainer. We're looking at something that's totally invisible to the human eye, yet it absolutely dictates our weather, our sea levels, and the economies of literally hundreds of millions of people. We're talking about a massive, hidden circulation system churning deep beneath the surface of the Atlantic Ocean. And recently, brand new data has completely upended everything we thought we knew about its stability.
Okay, let's dive into this. That number you're looking at, 20 million, it represents the cubic meters of water that this Atlantic conveyor belt moves every single second. To put that massive, almost incomprehensible number into perspective, think of the Amazon River, right? The largest river on planet Earth? Well, this single ocean current is moving the equivalent of 100 Amazon rivers, running simultaneously, all beneath the surface. It just continuously pulls warm tropical water north toward Europe and sends cold, deep water back south. It's an ocean engine of unimaginable scale.
Now, you might be wondering, what's the catch? Well, for years, the weakening of this ocean current, a system scientists call the AMOC, has been framed primarily as a future problem. It was treated as this distant simulation on a supercomputer that, maybe your grandchildren would have to worry about. But in April 2026, major studies published in Science Advances and Nature brought us a massive reality check. 4 physical sensors, resting right on the floor of the Atlantic Ocean, confirmed that a severe decline isn't some future forecast, it is a 20-year, ongoing, measured reality.
So, to really understand this reality check, here is our roadmap for today. First, the hidden ocean engine. Second, sensors versus supercomputers. Third, Greenland's freshwater lid. Fourth, a costly policy gap. And finally, number 5, the geographic blind spot. Let's get into it.
Section 1. The hidden ocean engine. Let's make the invisible physics of the ocean instantly understandable.
Oceanographers measure this flow using a unit called a sverdrup. 1 sverdrup equals 1 billion cubic meters of water moving past a point every second. At full strength, this Atlantic circulation moves about 20 sverdrups. But here's the crazy part. Over the last 2 decades, sensors have recorded a steady drop of roughly 2/3 of a sverdrup per year. Do the math over 20 years, and the current has lost roughly 14 sverdrups of power. That is literally the equivalent of 3 entire Amazon rivers just vanishing from the system.
And this brilliantly illustrates how the engine actually pumps. It's all about density. Step 1. Warm tropical water is loaded with dissolved salt. Step 2. When it gets up near Greenland, the freezing air cools it down, and because cold, salty water is heavy, it sinks. Step 3. As it sinks, it forcefully pulls more warm water up from behind to take its place. So think of it exactly this way. Cooling is the trigger, sinking is the downward stroke of the engine, and salt is the fuel. You take any of those away, and the engine misfires.
Which brings us to Section 2, Sensors versus Supercomputers.
So, if this engine is losing 3 Amazon rivers of flow right now, how on earth did official government models completely miss it? Well, for years, climate models projected the future by looking at either ocean temperature data or ocean saltiness data, almost never both combined against real observations. It's exactly like a doctor taking your blood pressure but never checking your pulse and then telling you your heart is totally fine. The April 2026 studies finally combined both variables and validated them against 20 years of actual physical sensor data from the ocean floor.
And when they did, the numbers shifted dramatically. The baseline estimate used by the IPCC and pretty much every government on Earth projected a 32% weakening by the year 2100. But the new combined sensor data pushed that projection up to 51%. That is a massive 60% quantitative gap. Now, the IPCC wasn't being sloppy here. They were simply using the published science available at the time. But once the new methodology was validated against 2 decades of physical sensor readings, the older, lower estimate just had nowhere left to hide.
Moving on to Section 3, Greenland's freshwater lid. There's a second major reason the old models came in so low. They missed a critical physical variable happening at the very top of the globe, right where the ocean engine does its hardest work. Now, what's really interesting about this slide is this staggering number, 280 billion. That's how many tons of ice Greenland is currently losing every single year. When all that fresh meltwater spills into the ocean, it just sits on the surface because fresh water is lighter than salt water. It acts like a massive lid, kind of like oil floating on water. It dilutes the salt, meaning the water doesn't get as heavy and it doesn't sink. The engine loses its compression. And here's the kicker. That 51% decline projection we just talked about, it didn't even fully factor in this accelerating Greenland melt.
This brings us to a concept scientists call the tipping point, the exact moment this weakening loop locks in and becomes self-reinforcing.
Scientists compare this tipping point to a seesaw. The sensor data confirms the heavy weight on the seesaw is creeping further from the center, and the seesaw is definitely tilting. But researchers don't know exactly where the definitive balance line is. As the quote says, it's like driving toward a cliff in the fog. You know you're getting closer, but you literally cannot see exactly where the edge begins.
All right, Section 4, a costly policy gap. Let's look at the real-world fallout. While we might not know exactly where the final tipping point is, the partial weakening is already producing very real, very costly consequences. As the ocean engine weakens, less water gets pulled away from the U.S. coastline, which accelerates sea level rise in cities like Miami and Boston. Get this, Naval Station Norfolk just spent $1.1 billion on flood infrastructure based on the old 32% projection. That means their brand new upgrades already have a confirmed safety shortfall built right in. The stalled ocean heat is also altering atmospheric patterns, causing massive marine heat waves in the Pacific, like the infamous blob, and disrupting the jet stream that dictates rainfall for wheat farmers in the American Midwest. The impacts are so severe that Iceland recently classified this current slowdown as a formal national security threat. So, the crucial point is this. The gap we're seeing isn't about scientific incompetence. It's a lag. The science simply changed way faster than the policy cycle. Every seawall, federal floodplain map, coastal zoning law, and insurance premium calculation was built on an older central estimate that sensors have now confirmed is 60% too low. We literally have tens of billions of dollars of infrastructure being built today against a baseline from the early 2020s that the science of 2026 has already corrected. And finally, Section 5, the geographic blind spot.
This brings us to a startling revelation about where we're actually looking to track these changes. Right now, every continuous monitoring station keeping an eye on this system sits in the North Atlantic. But a major nature study analyzed 1,300 years of deep ocean sediment records, basically the tree rings of the seafloor, and they found that historically, shifts in this massive ocean current were not triggered in the North Atlantic. They were actually led by the Southern Ocean, the waters circling Antarctica. In past climate cycles, Antarctica's waters changed first, and the Atlantic followed with a measurable lag.
Which makes this number somewhat alarming. The European Union has committed 180 million euros to research this Atlantic circulation through 2028. It's the largest coordinated research investment in the field. But that massive funding commitment contains absolutely zero dedicated monitoring for the Southern Ocean. The leading signal identified by a 1,300-year historical record remains completely outside our funded early warning network.
It leaves us with a glaring, confirmed blind spot. The sensors have proven the current is at its weakest point in 1,000 years. They've proven the official models were underestimating the decline by 60%, and they've proven that massive policy gaps exist in our infrastructure right now. But if history tells us the true warning signs start at the bottom of the globe, why are all our early warning sensors still anchored in the north?